So this is an exploratory problem set for periodic functions. So remember that periodic functions are functions that resemble or that rotates. Okay, so a circular motion which completes revolutions, or remember that one revolution is one circle. Okay, one circular motion. So if it completes a circle, that's considered a revolution. If it completes two circles, that's two revolutions. So the graph here that you see, the graph in figure 2-1c, is the graph of a sine function. Okay, so the sine function is abbreviated as sine. So as an introduction to trigonometry, you know, sine function with spelling of sine, this is sine function, and it's one of those periodic functions. This could also be pronounced as sine function. Okay, and it is written as a sine of an angle. So sine of an angle. So for example, in here our angle is theta, so we could write this as sine of theta, where theta is the angle. Okay? So plot your, now let's say your theta would be taken as x. Okay? So now your x would be in terms of angles also. So instead of theta as your angle, we are going to take your x. Okay? So if this is your x and this is your sine of x, well, x is in angle, so definitely we have to write your x in terms of angle. Okay? So let's say I am going to choose 0 and then 90 degrees and then 180 degrees and then 270 degrees and then let's say 360 degrees here because we missed one table. Okay. So after all this, what is our sine x? So our problem for 1 says that we have to plot our y is equal to, or y1 is equal to sine x, meaning this is our y1. So this is our y1 is equal to sine x. Now how do we plot our sine x? Because x is also theta, and theta is an angle, so this is also x, and both theta and x are angles. Okay, so I will write angular values for x. So those angular values are 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. So let's take a look on what happens to your y1 is equal to sine x. You could use your grapher, or if you don't have a grapher, you can use a scientific calculator. Just put your calculator to the mode of radian, or no need because you have the degrees. Okay, so if you put your calculator mode to degrees, then no need to put it into radian. So we are now going to compute for our value of sine of x for x is equal to 0. So if x is equal to 0, that would be y1 is equal to sine of 0, and that's equal to 0, right? So this is 0, while sine of 90 degrees would be, just erase a 0 and replace it with 90 degrees, that would be 1. Okay? If your x is 180 degrees, so just replace your 90 with 180 degrees, it would be 0. And if it's 270 degrees, that would be negative 1. And if it's 360 degrees, it goes back to 0. So now let's try to Let's try to graph it in this small space. Okay. So this would be our y-axis, and this would be our x-axis. And you could see that your y1 is equal to sine x is traveling from -1 for y up to +1 for y. Okay? So your x are in terms of angles. So your x definitely would be angles. Okay, so instead of numerical values here, instead of numbers, or instead of integers, we're going to write the angular values. So this is 90 degrees, this is 180 degrees, this is 270 degrees, this is 360 degrees. And notice that our y values are restricted from 1 to -1 because that's the maximum value for y as your x ascends from 90 degrees. And 90 degrees means that if this is your circle, your 90 degrees would be the maximum part, and your 270 degrees is the minimum part. So this is 90 degrees, right? Add 90 degrees, that's 180 degrees. 180 plus 90, that's 270. 270 plus 90 is 360. So therefore, our 270 is this portion. Okay? So in 270, you have a minimum at -1. At 90 degrees, you have a maximum at 1. Okay? So that means that we're going to write +1 or -1 here. And graphing the points, okay? So graphing the points, this will give us, for 0 degrees, we also get a 0, so it's here, okay? For 90 degrees, we get a 1, so it's here. For 180, we get a 0, so it's here. For 270, we get a -1, so it's here. And for 360, we get a 0, which is there. And connect them by, a smooth curve. So connecting by a smooth curve should give us a plot which is this is thick, so I want this. So it will give us a curve that is like that. Okay, and that is one period. Okay, remember that from 0 we completed one circle. So this is one circle from 0 degrees to 360 degrees. That's one complete circle, or that's one revolution. So that's one period for the sine function. Okay, and of course it will still continue. So it will go like that, and it will go like that. Okay, so this is your sine function. Okay, now if you're going to use a grapher and extend your theta to at least 3 circles, this is one circle, this is 2 circles, so we have 2 circles here. So if we're going to extend your theta up to 2 circles or up to 720 degrees, then that would be the formation of the sinusoidal graph, or the function of your sine theta or sine x. Okay, so we have done the graph of our sine function, and we use the manual graphing for this, but you can also use the grapher to confirm this value for your sine function, this x values and y values for your sine function. Number 2, the graphs in figures 2-1b and 2-1c are called sinusoids. So pronounced like sinus, a skull cavity. So what 2 transformations must you perform on the sinusoid to get the sinusoid in figure 2-1b? So from 2-1c to 2-1b. What is our 2-1b? This is our 2-1b. If I'm not mistaken, yes. Yes, this is our 2-1 b. Okay, so how do we go to this function or this graph? This is 2-1 b, and this is our 2-1 c. So how do we go there? Look, from here, from here, notice that our line of symmetry, okay, is in the x-axis, or when y is equal to 0. Now it seems to have a line of symmetry here at y is equal to 11. Am I correct? So before the other graph, so let's draw an image here. It is from the line of symmetry is in the y-axis or x-axis. It's in the x-axis, right? So x, y. But now we have a line of symmetry, which is y is equal to 11. So how are we going to transform the equation of the sine function, sine x? So remember our graph for 2-1b. So first, this is y is equal to sine, y1 is equal to sine of x. And this is figure 2-1 c, and this is 2-1b. So we have to translate this into a certain equation so that our graph would look like translated to the y is equal to 11. Okay? And this is a translation, a vertical translation to say the least. Okay? So what are we going to do then? Because this is a translation, we have to make use of our skills in translating. Okay? So y2, let's call this y2, and it is translated vertically upwards. Okay, so it will be translated. There is no lateral translation, meaning we don't have a horizontal translation. Okay, all we have is a vertical translation, 11 units up, because our axis of symmetry changed to 11. So this will have a value which is, or a function which is sine x plus 11. Am I correct? With our value for this would have, so sine x plus 11. But still, aside from vertical translation, we also have a vertical stretch. Look at your values here from 2 to 11. Look at that. Well, in the original, you know, the maximum here is 1 and the minimum here is -1. So the distance from your axis of symmetry to the maximum or the minimum is 1. But in here, it changed. Look at your stretch. It stretches to 9 times of your original. Am I correct? So we therefore have a vertical stretch which is 9 times of a factor. So we will have to write 9 here. Okay? So that's how we translate this original function y1 is equal to sine x to this sinusoidal graph 2-1b. So that's the answer for letter B, or number 2. So next, enter in your grapher an appropriate equation for the sinusoid. So we already did that. So that is y2. Now you can check, okay, using the sinusoid, your grapher to look for this sinusoid. Okay, so this is number 2 as well as number 3. Okay, next, number 4. Explain how an angle can have measure of more than 180 degrees. Explain the real significance of the negative values of theta in figures 2-11 or 2-1b and 2-1c. Okay, so first explain how an angle can have measure of more than 180 degrees. Okay, so as I've said, and as I have introduced, so let's take a look here. Okay, let's draw a circle. So this is our circle. Okay, and this circle has absolutely, if we're going to divide it into four, okay, and your position will be placed, let's say here. Okay, this is your position. So if we are going to rotate it to 180 degrees, you could use either you can use your scales. Okay, you can use your protractor. You can use any angular measurement device. So 180 degrees is here, right? And 180 degrees is half a circle. Am I correct? So half a circle is equal to 180 degrees. And full circle is 360 degrees. Now, because theta, here theta defines the angular measure from a certain position, from an initial position to a terminal position. Initial means where you came from, to a terminal position or where you are heading. So in this case, your theta could actually extend. So from 180 degrees, it could go up to 270 degrees. Why this is 270 degrees? This is because this 180 degrees will add up to a 90 degrees here. Am I correct? This is 90 degrees. This is 90 degrees, so that's 180 degrees. And another 90 degrees gives us 270 degrees. And therefore, another 90 degrees going back to the original position will give us 90 degrees. So that is approximately, or that is exactly 360 degrees. So we have completed a full circle or one revolution. So that's how in real world, as in this case, your rotation, your angle could go from more than 180 degrees. It could go up to 270 or even up to 360 degrees and so on. Okay, so that's the full explanation for number 4, how an angle can have measure of more than 180 degrees. Now, explain the real world significance of the negative values of theta in figures 2-1b and 2-1c. Well, this real world significance is that in the Ferris wheel, again, in this Ferris wheel, when at a point in time where you go to here 270 degrees. Look, in the Cartesian coordinates, you have x here, you have y here, and when you go here to 270 degrees, you get a negative value, right? That's a minimum. Okay, so the real world interpretation is when you go to here, look, you are below. So meaning that's like in Cartesian coordinates, that's a negative. Okay, because we take our axis of rotation, and therefore our center here on the running through this fulcrum here, okay, or the pivot point. So that's why we can have a negative value for x is equal to 270 degrees, and also for x is equal to 90 degrees for the sine function. For this sine function, we have +1 and -1. Okay, so that's the answer for number 4.